This is a video for MEI Core Pure Mathematics, Calculus 1 Improper Integrals, 1.2 Integrals with Infinite Limits Divergent. We saw in a previous video that by an improper integral we mean one where we may have a limit of infinity, and this integral here is the integral between 2 and infinity of 1 over x dx. And we can see that as x tends towards infinity, the value of the function continues to reduce. And indeed we know that in the limit it tends to a value of 0. The question then is, what happens to this area? Does it tend to a limit, or does it head off towards infinity? To look at that, we need to consider what happens at the limit. Here's our integral. I'm going to change that to the integral between 2, and I'm going to replace the upper limit, the problem one, with a variable a. So this is 1 over x dx. And then this upper limit, this problem limit, I'm going to allow the variable a to tend to infinity. Well, the integral of 1 over x is simply log of mod x, and that's between 2 and a. And what happens as a tends to infinity? Well, plug in those values. From the upper limit I'm going to get the log of mod a, and minus from the lower limit I'm going to get the log of 2. And what happens as we allow a to tend to infinity? Okay, so if a tends to infinity, what happens to the log of a? Well, that too tends to infinity. And so this bit of our result does not tend to a limit. And therefore we say that this integral is divergent. There's that working tidied up. So we can see here we replaced the problem upper limit with a variable and then allowed that to tend to infinity. And down here we've looked at, after we've done all the integration and substitution and so on, we look at what happens as a tends to infinity, and it turns out that the result does not converge. So the integral is divergent, it's not defined in the limit, and it therefore has no numerical value. So here are two functions that we've looked at in this video and a previous video. They're very similar. They both tend towards 0 as x tends towards infinity, and we're interested in the area underneath these curves between 2 and infinity. Let's have a look at another way of determining whether they're convergent or divergent. Here's a plot of those two functions. The red line is the function y equals 1 over x, and the green line is the function y equals 1 over x squared. These two numbers at the bottom here represent the area under the red function and the green function between a and b. Let's watch what happens as we raise the upper limit. You can see that both values are increasing, although the red one is increasing much faster. And as we push on up the scale, you can see that actually the green number is starting to settle down. And it takes a long time to make any movement, whilst the red value continues to push on up. In fact, the green value stays under a half. And we know that for that green function 1 over x squared, the integral between 2 and infinity has a limit of a half. The red function 1 over x does not tend to a limit and will continue to head towards infinity. So back to our functions then, and we know that this one is convergent. And we have seen by two techniques that it actually tends to a limit of a half. This function is divergent, and it does not tend to a limit. It is, however, very difficult to know what's going on unless you look at the limits as we have done in these two videos. So the technique overall: replace the problem infinite limit with a variable and then allow that variable to tend to infinity once you've done the integration. The next video in this sequence is integrals with a function undefined at a limit.